Good morning, my dear students. So, in this video, I will be discussing the second lesson this quarter, known as the Coulomb's Law. In this lesson, we only have one simple learning target, and that is to calculate the net electric force on a point charge exerted by a system of point charges. Okay, so I hope the video is visible. Okay, and I want you to follow through the discussion. And I hope you are equipped with necessary materials such as your calculators, notebooks, or scratch papers for problem solving later on. Okay, so in the spirit of the month, the love month, if you notice, our PowerPoint is pink. Okay, and I shall begin this lesson as well with a story. Okay, so I hope everybody will participate. I would like you to close your eyes and really close your eyes, okay? And then I want you to visualize the story that I will be depicting. Okay? So you listen carefully to my story and you imagine the scenario. Okay? So if you're ready, close your eyes and let's begin. So imagine a vast empty space. And in this vast empty space, there is a lone negative particle or an electron. This electron is just swirling around, moving around, traversing the vast empty space. And then, suddenly, the electron meets a positive particle, say a proton. And them being of different part nature, one is positive, one is negative, they felt an attractive force. The electron specifically felt a force that pulls it towards the positive particles. Similarly, the positive particle got attracted as well to the negative charge. Isn't that quite interesting? And then, because there's this attractive force pulling them together towards each other, interesting, they started to move closer and closer to each other. But as they move closer to each other, the strength of that attractive force grew higher or bigger and more massive in magnitude. And wouldn't it be interesting to determine the magnitude of that attractive force between the two particles? And so I'd like you to open your eyes and look at the PowerPoint. Yeah, you'll see in the PowerPoint we have two particles that experience an attractive force in different directions, opposing directions, yet towards each other. And today, we will be using the Coulomb's law to determine the magnitude of this attractive force. Now, a disclaimer, the force I'm depicting is attractive because we have two particles that are opposite in signs. Okay? So, what is the Coulomb's law? The Coulomb's law is a mathematical equation that allows us to calculate the magnitude of that attractive force or repulsive force in some cases. And in the equation, you will see the variables k, q1, q2 are squared. Okay, so Coulomb's law um, is used to calculate the magnitude of the force between 2 point charges known as q1 and q2. Remember in our previous lesson, we associate the symbol Q to charged particles. And these charged particles are separated by a distance r. So whenever you see r in an equation, that represents distance, a separation distance. Also, you will see the letter K, which is actually a constant, a Coulomb's constant, which has a magnitude of 8.988 times 10 raised to 9 newtons meter squared per coulomb squared. But in our equations or solutions later on, we can use a rounded off version of this constant, which is 9.0 or 9 times 10 raised to 9 newtons meter squared per coulomb squared. And this is the equation that you will use in order to determine the magnitude of the force. Let's change the color for a while. A few points to remember before we actually do the computations. This force, by its equation, has certain implications. If you noticed earlier, the formula has a denominator r squared. Okay, and since the formula is written that way, it simply indicates that the relationship between the separation distance and the electrostatic force or electric force is inversely proportional. That is the hold on, which means that the farther the particles are, charged particles are to from each other, the weaker is the electrostatic force. And the closer they are to each other, the greater is the electric force. Again, this is an implication of the variable r squared in this equation. So K Q1, Q2 divided by r squared. Okay, simply means that the higher the distance, separation distance, the lower the electrostatic force. Okay, so the attractive force is weaker when they are farther apart, and the electrostatic force is greater when they are closer to each other. This is similar to certain relationships we have, right? If you are attracted to a certain person, the closer you are, or the more frequent you are together with that person, the greater is the attraction, right? And if, let's say, you are not that close to that person, you are not of the same nature, say you are like two similar charges, two positive particles, for example, then you would repel each other. And the implication would be, since you don't like each other, the closer you are to each other, the more frequent you are together, the more you'd feel the repulsion or repulsive force. But the farther you are, the weaker is the repulsive force. It's better that you are not together because you don't like each other. It's like that in some sense. No, we have discussed this electrostatic law last meeting, that like charges repel and unlike charges attract. So if you have a positive and a negative particle, they would attract, and two like charges, positive and positive would repel, negative and negative would repel. This law applies still for this current law that we are studying. Okay, so the attractive force is greater when two unlike charges are closer to each other, and it's weaker when they are farther apart. And the repulsive force is greater when two like charges are closer, and it is weaker when they are farther apart. So the same law still, or the initial laws we studied, still applies for this problem. Okay. So we have discussed attractive force. And one of the common attractive force that we know and experience would be the gravitational attraction between two heavenly bodies. For example, the sun and the earth. They are constantly attracted to each other, no, by what the force known as the gravitational force. For example, the sun has a certain mass m, and the earth has another certain mass m, small letter m, and these two masses exert a force, to attractive force, towards each other, which can be calculated using this formula. F is equal to g times m, capital M, times small m over r squared. If you look at the way the equation is stated, this is very similar to the Coulomb's law, because this law is like a restatement of the Coulomb's law, or vice versa. But instead of having charges, Q1 and Q2, you have masses. Okay? Um, Similar to the Coulomb's law equation, you have a Coulomb's law constant. Here you have a gravitational constant with a certain value, 6.68 times 10 raised to negative 11 m cube per kilogram seconds squared. Okay, so what's the implication of this? The gravitational force is like the electrostatic force, but the only difference is that the gravitational force is always and only an attractive force and never a repulsive force. Hindi mo naman nakita yung Earth, right, or any planet in the solar system suddenly expelled out of the solar system because of a repulsive force from the sun. You see, all of the planets stay in place because of this attractive force toward the sun and never a repulsive force. It's the same as when you have an object lifted on the surface of the earth. For example, this cup, I lift this up, and so I am separating this mass from the mass of the earth. But once I let go of this cup, which I won't, we know that this particle or cup will move towards the earth because it's feeling an attractive force. This mass feels an attractive force from another mass, which is the earth. Okay, this will crash towards the earth. But we learned in the previous discussions that the falling motion of any object here on the surface doesn't always indicate that the object falling is the only one attracted to the earth. We know that the earth is also attracted to that falling object, and so both are crashing towards each other actually. But the earth is so massive that you will not be able to see or feel its motion. Okay, the only visible motion would be the motion of the lighter mass or object. Okay, and the gravitational force is way, way weaker than the electrostatic force. I already distinguished this last quarter that although gravitational force is the most evident of all the forces that we have, it's actually a very weak type of force. Okay, and electric force is the force that holds and binds subatomic particles together. So it's very strong compared to this type of force. Moving on. Okay, so to continue the lesson, I'm so sorry, you could see the cross right here. So you'll know that this video was recorded during the Ash Wednesday, Wednesday Mass. Okay, so to continue, we have this principle known as superposition principle. Because when we talk about electric force, it's not a force just between two charged particles. You could have several charges interacting as a system. When we say system, um, we consider only isolated systems. Those would be um, one example would be the solar system. In the solar system, you have several planets and the sun at the center, and all of those planets and the sun interact as one system, and that their movement, motions aren't affected by other factors. Okay, only by their attraction to the sun. So this is known as a system. It's a closed system. Okay, in the absence of other forces. Now, we would also consider certain scenarios, such as a system of charged particles. You could have several protons and electrons interacting without the effect of external factors. Okay, so for example, on the screen, we have three charges. Charge Q, the capital Q, the red circle indicates, let's say, a positive charge. Let's change the color of the pen. Hold on. Hang on, hang on. All right. Sorry. All right. So for example, we have this particle charge Q, the capital Q, which is, say, a positive charge. And then we have other negative charges present in the surrounding. For example, this is the closed system that we'll consider a a three a system of three charged particles. And then we have the negative charged particles exerting an attractive force on the positive particle. Why attractive? Because they are different in nature. And we all know, as mentioned earlier, that like charges repel and unlike charges attract. So we know that charge Q1 right here, the blue one, and then charge Q2, the other blue one, are gonna exert an attractive force with respect to the positive charge. So they are supposed to pull the charge into their direction. But obviously, we cannot split the positive charge into two, just so the charge 1 and Q1 and Q2 would attract them, right? Now, what will happen is that the possible motion of the positive particle will be based on the effect of the two negative particles. So instead of being attracted just to Q1 or just to Q2, the particle will be attracted to both, causing it to move in a path that is, in a way, at the center or in between charge 1, Q1, and Q2. And this is known as the superposition principle, wherein the sum of forces on each charges is the vector sum of all contributory forces of all the individual forces. So all the individual forces present right now, as exerted by Q1 and Q2, will be added, and that the sum of their forces will be the one that will cause the motion of the positive particle. So if you think about it, there is a force in this direction, which is the force of Q1. Okay. At the same time, there is also an attractive force in this direction, force 2. But we know that the particle will experience the sum of the two forces, and that would be the force at the center. So we will call this the net force, or force, the summation of the two forces. And this, there's a more rigid math for this. And so we're going to save this type of problem next meeting. Okay. We will only consider in this lecture video a 2-point charge example. Okay, meaning to say my examples will involve only two charges. Okay, so moving on. Moving on. Okay, hang on.